it's no fun to verify programs unless you can run them. And it's not that much fun to run programs inside Coq. So let's talk about extracting programs from Coq and running them in your favorite functional programming language. As long as your favorite functional programming language is either OCaml or Haskell. Neither of those are my favorite functional programming languages, but they'll do just fine. So there's a extraction feature in Coq, and I will show you how to use it, and then we'll extract red-black trees and run them on some inputs. Search trees, binary search trees, unbalanced binary search trees. So let's look at the extraction mechanism. We'll start with insertion sort. Here's our little insertion sort program that I lectured about, was it only yesterday? And we require the Coq extraction module from the Coq standard library, and then we use the command extraction sort. And you can see it prints out an OCaml program for the sort function. You can set some settings in extraction to get Haskell instead. And this, notice, is OCaml syntax. Okay, so the sort function by itself isn't very useful without the insert function. So let's do recursive extraction sort. And that gets us all the things that sort depended on, which turns out to be not only the insert function, but the LEB, less than or equal Boolean type on natural numbers. And you can see that, well, this should look familiar. You did this in Coq, in the Coq intensive. And then the list type, which is the translation of Coq's inductive type list into OCaml. And then the nat type, which is the translation of Coq's inductive type nat into an OCaml data type, and so on, and similarly for bool. Well, if we're going to interface this extracted sort function that we proved correct to other OCaml code that we didn't prove correct, maybe because it does useful things like I/O, then we would like our function to use Coq's standard, OCaml's standard list type and OCaml's standard bool type, and so on. And to do that, we can give an extraction directive. We can say extract Coq's inductive type bool as OCaml's bool type, and use the true constructor for true and the false constructor for false. And you better list these in the right order, otherwise it doesn't mean what you think. This is quite dangerous, right? We can't prove anything about extract directives. You better know what you're doing, otherwise if you get it wrong, then all your proofs are useless. And let's extract list as OCaml's list type with this operator for nil and this operator for cons. And then let's do recursive extraction sort. And notice that it's using OCaml's native lists and OCaml's native Booleans. Great, but it's still using unary representation natural numbers, which is not so much fun. So we want to extract natural numbers as what? I don't know. We could give an extraction directive saying extract natural numbers as OCaml's native integers and use +1 for S and 0 for O. That would be quite dangerous because there are some things you can prove about the natural numbers that are not true of OCaml's native integers. For example, you can prove that every natural number has a successor that's greater than it. Okay, and that's not true of OCaml's fixed precision integers, which wrap around. So then you've got an inconsistency, and you can prove properties of your algorithm that aren't true, and you're in big trouble. So I'm going to show you the way that I recommend you do this. Let's have an abstract type int. Okay, so parameter outside of a module type really just adds a completely abstract value to the system. So this is an abstract value of type, so it's an abstract type. Right now, with just the parameter int, we haven't added any inconsistency yet to Coq. Whenever you add an axiom or parameter, you might be adding inconsistency. But just the existence of some type is not itself inconsistent. And then we can extract that inline constant, that constant to the OCaml int. Okay, so we mean this to be the OCaml integer type. Now, we're going to add an axiom about OCaml's integer type, that it has a less than function that compares two ints and returns a bool. This seems not too dangerous. That there could be an abstract type int that has a relation. Okay, that doesn't seem like it's inconsistent with the calculus of inductive constructions, but we don't have a proof that it's not inconsistent, at least not a machine-checked proof in Coq. We're trying to be careful here. And we will extract LTB as OCaml's less than function. So far, so good. But now, we need to reason in our proof about the less than. We're going to need the properties of a total order. So, here's how we're going to do that. I'm going to add this parameter saying there's a function that maps integers to z. Z is the mathematical integers as constructed in Coq's calculus of inductive constructions. Okay, so does it seem inconsistent that there could be some function from int to z? Seems reasonable. I could make the function that always returns 0, for example. No inconsistency yet. And let's axiomatize that function as follows. Okay, well, this is yellow. All these things are yellow. When you add an axiom or a parameter to Coq, which could possibly cause inconsistency, Coq IDE highlights it in yellow. I don't remember what color Proof General uses. I'm not sure Proof General does highlight it in a color. But anyway, here's our axiom. LTB nm equals true if and only if int to z of n is less than int to z of m. Okay, now, this could be an inconsistency, so let's see if we believe that this could be reasonable. Int is the 31-bit 2's complement integers where the arithmetic wraps around, right? So the axiomatization of plus is actually quite complicated. But we're not axiomatizing plus. We're axiomatizing less than. So do we believe there's a function from the 2's complement 31-bit integers to the mathematical integers? Yeah. Seems reasonable to believe that the obvious sort of interpretation of a 2's complement number could be what we want here. And then do we believe that OCaml's less than comparison on those 31-bit 2's complement integers corresponds to the mathematical less than comparison on what they represent? That all seems reasonable. There's no worry about the wraparound of modular arithmetic because we're not adding and multiplying and subtracting. We're just comparing. Okay, we're done with axioms. Every time we added an axiom, it was dangerous. It's good that we're done. We're past all the danger. We believe all these things. Maybe they're even true, meaning maybe they're even consistent with the calculus of inductive constructions, and therefore, whatever we proved about search trees will actually be relevant to the operation of software. Okay, now, so now we can prove some theorems. That we can remember our friend reflect that relates a proposition to a computation. So the computation here is OCaml's less than comparison of these int 31, x and y. And the proposition is that the mathematical integer that x represents is actually less than the mathematical integer y represents. So we'll reflect that. So we can do our b-destruct on these guys, right? And we can prove this using LTB-LT, which is that possibly dangerous axiom. So once we've got the one possibly dangerous axiom, then everything else from now on is a theorem, right? That it reflects properly, the less than reflects, the equal reflects, the less than, this is just a reflection on mathematical integers. It doesn't involve the axiom at all. We put that into our hint database for bdestruct, and now we can use bdestruct just like you already used it in the proof of insertion sort. By the way, how many people completed the proof of insertion sort? Good. How many people made some progress into it anyway? Good. Now, and I claim that the proof of, a couple of theorems about lookup and insert in binary search trees is not going to be much more difficult than that, and you can do it. Okay, so we're going to just redo binary search trees, but using this key type, int, rather than nat. So all this stuff here you've seen before. It's just you saw it with natural numbers, and now we're doing it for this other key type, key : int. So the empty, lookup, insert, elements prime, elements, combine, all this is just the same. The theorems are the same. If you really wanted to prove these, you would just paste in your other proofs and adjust the types where necessary. But I don't want to talk about the proofs here. I want to talk about extraction. So when we do abstraction, here's our OCaml lookup function, which is just the OCaml translation of the Coq lookup function. So very straightforward. And actually, we can extract this into an ML file. It's not so useful to have it printed out here in the window of our interactive development environment. What we really want is an ML file that we can compile. Okay, so let's run OCaml. Here I write some OCaml code that's a driver for the Coq code. So this insert is calling the insert on binary search trees extracted from the Coq code. And this lookup, same. And the empty tree also. And so we, we use search tree.ml. That is exactly this extracted code, right? And then we use test search tree.ml. Oops. Okay, and it's running some tests. It's taking a while. What's happening here? This test driver, you give it a parameter n. Here I gave it 1,000,000, and it inserted 1,000,000 random integers, each between 0 and 1,000,000, into a search tree, and then it looked up 1,000,000 random integers, and the whole thing took 1 second. And I don't even remember whether the OCaml I'm running here is the bytecode OCaml or the native code OCaml. But whatever. Here, if we just do 20,000 random integers, it only takes 15 1/100ths of a second. But suppose I insert 20,000 consecutive integers. I insert the integers 1, 2, 3, 4, 5, one at a time in that order into the binary search tree. And then I look them up. And that takes 4 seconds. So this takes 28 times as long, it looks like, as the 20,000 random integers. Why is that? Well, when we insert consecutive integers into a binary search tree, it becomes very, 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 very unbalanced. Or even very, 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 very unbalanced, because, let's see, the 1 would go here, and then the 2 would go here. Well, the 1 would go at the root, right, and this is empty. And then the 2, and then the 3, and then the 4, and then the 5, and then the 6. So we have a completely unbalanced, the maximally unbalanced tree, and then we look things up in the maximally unbalanced tree, and it takes a long time. So we want balanced binary search trees. We could use AVL trees. There's an implementation of AVL trees in the Coq library. AVL trees were invented in approximately 1960 in Russia by Adelson, Bielski, and Landis. Or we could use red-black trees, which were invented in California, I think, in 1978. And we'll use red-black trees, because this is America. Actually, Jean-Christophe Filiatre asked me a couple of years ago, why do you Americans like red-black trees so much? And AVL trees work perfectly well in our Coq implementation. They perform well and so on. And I said, I don't know. Let me go home and ask Sedgwick. So I asked Bob Sedgwick. Jean-Christophe says, why do you Americans like red-black trees so much? And Sedgwick says, the rebalancing of red-black trees can be done in a top-down pass, especially in an imperative implementation. You don't have to do it on the bottom-up pass after the insert. And that means that if you have a concurrent shared memory database system, the locking can be done a kind of hand-over-hand locking, and you increase the concurrency. Interesting answer. All right, so it's America, and we'll do red-black trees. So let me tell you about red-black trees using somebody else's slides, by permission. Okay, so there are binary search trees, and each node is colored red or black, because in 1978, when they wrote the paper about red-black trees, and they had to print it on the impact printer, and you had a two-color ribbon with red and black on the ribbon. Raise your hand if you were around in 1978 and you remember printer ribbons like that. Okay, not many of you. Okay, so the colors are arranged in such a way as to enforce the property that the height of the tree is no more than 2 log n. Okay, and so every node is either red or black. Every leaf is black. If a node is red, both of its children are black. That means on the path from the root to a leaf, you never have 2 red nodes in a row. But black nodes can have black children. That's okay. And the root is black. So those are the properties. And from that, well, you know, if there are never 2 red nodes in a row, then the height of the tree, well, think about just the black nodes in the tree. That's a complete binary search tree, because the number of black nodes on every path from the root to the leaf is the same at every leaf, right? Now you insert some red nodes here and there. That can increase the height of the tree, but never by more than a factor of 2, because there are never 2 red nodes in a row. So the height of the tree is never more than 2 times the length of the black node path. And the length of the black node path, well, the black nodes themselves form a complete binary tree, so that's just log base 2 of n. So that's a proof. We're not going to prove that in Coq, and here's why. Actually, we are going to prove that in Coq. I forget. Yeah, I have a proof of that in Coq. Okay, so let's color this tree. How can we color this